All right, so this is, just so you're aware, this is now recording. And so Michaela can see we've just gone from. Now, this is an extension 2 book, so different to a lot of the other books. It just keeps rolling on and on and on. It gets to question 19 in the previous exercise and then just starts the next thing. Whereas in a lot of the other textbooks, it'll start on a new page. So just to let you guys know, it is recording. You will be heard on here if you're talking, okay? Which is not a problem. So you can all say, hi, Michaela.
Hello, hi, Michaela.
So as you guys said earlier, the plan is to get through as much of this topic as possible without her here, because that way you've got more of a chance of beating her.
Yeah.
Nice. I like it. All right. So Argand Diagram, I haven't highlighted it a lot in this, mainly because it is fairly self-explanatory once we get into it. So Argand Diagram, we've already talked about, I'll talk about the unit circle, but actually, realistically, with this, you're more talking about the number line. So when we deal with the number line for real numbers, you're talking about a horizontal number line. You can see it highlighted there, not 1, 2, 3, 4. You can go into the negatives as well. We normally just deal with integers on a number line. Like if you see a number line, normally you've got 0, 1, 2, 3, all that. You can deal with fractions on them, especially if we're talking about things like probability. We'll throw in halves and stuff like that. But it's important to realize that the number line can include every real number, whether it be an integer, whether it be a positive and negative, or whether it be an irrational number. So the square root of 2 being irrational, pi being irrational, still exist on the real number line. They do exist in there. So square root of 2 is 1.14 or whatever it is. It sits in between 1 and 2. So it can be plotted on a normal number line. Sure. So we've got fractions, and numbers like e are on there as well, which is Euler's number. Okay. So it's just a number plane. Every number in existence, all the real numbers can exist on there. So here is where we start to go, okay, well, what do we do with imaginary numbers? And that's why we start to think about having the vertical axis as well. Okay, and that's why I liken it to the unit diagram, because we've got that. Yeah. But we've run out of space on the real number line. Okay, we've used all of the things. We've got everything that we can there. We cool with that?
Yep.
All right, so what do? We go, well, you know what? We'll add another plane to it. So we're going to add a complex plane. So rather than trying to squish more stuff, we've gone, here is the horizontal plane. It represents all the real. And now what we'll do is we'll do an imaginary plane, or a complex plane, with the imaginary axis, and then we've got a way to put it on there. And we've already talked about how you would plot that on there. We plot it with a real and an imaginary. So you just use a coordinate system like we've already got. So we do it in the form of z equals x plus iy, where x is the real part and y is the imaginary part. And then we just plot it like we would a normal point, a normal coordinate. It doesn't have to be an x, it doesn't have to be a y. In fact, most of the time we won't refer to them as x and y. But that's kind of what they are. I hesitate to say that I assume you know, but I assume you know how the Cartesian plane got its name.
Cartesian.
Close.
Cartography.
It did get. Cartography and Cartesian have the same root.
I assume it's a guy's name.
It is a guy's name.
Ancient Greek guy.
No, French. Oh. I think, therefore I am.
Oh,
René Descartes.
Yeah.
So he was the one who pioneered cartography, came up with the idea of the Cartesian plane. This other guy, who is Jean-Robert Argand, or Argand, came up with the idea of using an Argand diagram. So he basically said, hey, let's use an axis, and that way we can plot complex numbers on it.
Right.
So that wasn't that long ago, if you have a look at it, 1768. So it's not that long ago. In fact, that wasn't very far after, and I mean, obviously it had to be after, but that wasn't very far after the idea of zero was established, because zero is not that old. Zero is a number that, well, the Jesuit priests of the Catholic Church tried to disprove the existence of zero.
Yeah.
They used a bloke named Aloysius. You may recognise that from the school, St. Aloysius, down in Sydney, which is a very prestigious school. He was tasked by the Vatican to go and disprove the existence of zero. Why would the Vatican want to disprove zero? That seems like a weird process.
Oh,
What is infinity?
God.
There we go. What is the opposite of infinity?
Zero.
Nothing. There you go. And that was the whole thing. Disprove it, please. Get rid of it. Unfortunately, what he did was he proved it and showed that it was really useful. And the Jesuit schools is now the teaching side of the Catholic Church. So, because they went, hey, we're actually probably better at doing this than doing that. So, yeah. But so zero is not that old.
But how do you do maths before zero? Like 1 minus 1 is just
Nothing. But it was the whole concept, because it was like infinity is not a number. Infinity is a concept.
Yeah.
Okay. So
It's like you wouldn't use infinity in an equation.
correct. Other than limits.
Yeah.
Sorry. There's a mathematician, I can never remember his name, he's a German mathematician, went nuts. Okay. Because he was studying the existence of infinities. And what he did was he proved that some infinities are bigger than others. How many numbers are there between 1 and 2?
Infinity.
And an infinite amount, because you've got all the fractions and all that. How many are there between 2 and 3?
infinite.
Okay, what about between 1 and 3?
Infinite.
Well, you've got 3 lots of infinity.
Well, that's still the same amount of infinity, though.
Is it?
There's a different.
It's a smaller. It's
But
a
you've
bigger
got
infinity.
you've got
There's
the
a
set
way-
of between 1 and 2 is a subset of those between 1 and 3. Isn't a subset by definition at least smaller. So the set has to be as big, if not bigger. That is the definition of a set.
Yeah.
So it was one of those things that he was trying to show that, and he went nuts. He was obviously a little bit nuts to begin with.
But, yeah, it's the same. I saw something that's the same amount because you can line all the numbers up. But then if you move, like if you,
That's a really good video.
yeah,
Yes.
I can't remember exactly. What
Countable infinities and uncountable infinities.
But
So there are some that are countable because you can line things up against them and assign a thing against them, and there's others that are uncountable.
No, if there's a hotel with infinite rooms
I saw
and
that.
every room is
I
filled,
saw that.
Yeah.
can you fit one more person?
Yes. You just get everyone to shift down one.
Yeah, and this is one of the great conversations we have with students. What's the biggest number you can think of? All right, now add one. You've thought of a bigger number. Like, yay, you've learned something today. So but we're getting off the topic, but this is how zeros was just a concept. It was just, I don't have any. So the thought process was, because, 1, 2, many. So a lot of time for the counting, it was just 1, 2, many. And then you had 1, 2, 3, and a handful. And that's where we got numbers like a gross, a score, a few, a dozen. Do you know what a gross is?
No.
It's a dozen. So it's 12 squared. So it's 144. So, yeah. So we came up with names for things as we needed them. And zero was one of those ones that we didn't really need to assign a number to it because we had a name for it. It was just nothing.
Yeah.
And
I don't have any.
yeah, I don't have any. Yeah, there wasn't a need for a zero. There's actually a shrine in India where the first written zero is, and it's on a tablet there. And it was actually used so that they could calculate how much square meterage or how much area they needed to have under planting for flowers to keep fresh flowers in the palace every day. So they were calculating areas, and so that's what they were using it for. That's when the first noted existence of zero is. So it's pretty cool.
Yeah.
Yeah. Anyway, so we obviously had to have zeros before we could do either the Cartesian or the Argand. Okay. So this one's named the Argand. We can also call it the complex number plane or the Z plane, which is a stupid name. But that's all right. All right. So when we do an Argand point, a lot of the time we'll call it Z, X, Y, and we'll give those to it. That'll be point Z. And that means it is in the form of X plus something I. Or X plus IY. But a lot of the time we don't write it. Pretty straightforward, the real and imaginary axis. If the imaginary part of a number is 0, it just means it's got 0i. If the real part of it has 0, then it's 0. The x is 0. And it lies on the vertical axis. While you're doing that, I'm just going to, I don't know if I pause this, I wonder what it'll do, because I'm actually recording this application, this window, rather than just my computer. So if I was showing you something on the web, it wouldn't come out on the video. So let's see, is it still recording? Yeah, it seems to be still recording. It's been going for 10 minutes now. That's good. All right.
Yeah, it's interesting.
Sometimes you need to get like the background stuff. Once again, explained to the which was it, the year 8s maybe. Oh no, it was the year 12s. Sometimes like you get people that like or dislike your teaching, and that's fine. But we were talking. Oh, that's right. We were talking about performance-based pay. So the better your kids go in assessments, the more money you get paid. And
Yeah, that's fair. Oh, sorry, no, it's not.
imagine
No, it's not.
how that would change
Like-
the nature of teaching.
As in, I think you could only do that for HSC. You couldn't do that because otherwise you just set easy assessments.
There you go. Or you, and even for the HSC, I would go, right, here's past HSC papers. All I'm going to teach you is the stuff that's shown up in them. I'm not going to worry about background content. I'm not going to worry about like some of the stories that we do tell to try and give you some context to where it sits. I wouldn't worry about practical applications of it. I would just be teaching to the test. I wouldn't, because I don't care about the money. If I did, I would still be a graphic designer, but that's a different story. But yeah, it would change the nature of how a lot of teachers teach. And I don't think that'd be a great thing.
Yeah.
So, having said that, I'm sure some of the students would go, yeah, no, it'd be great if you just shut up for a while, mate. Thanks, Michaela. All right.
Hopefully, it's recording audio.
Yeah, it does.
Okay.
Because I use this to record YouTube videos of worked examples.
Oh.
I'm going to start doing that for you guys as well, just so you can refer back to them. I should actually do it while we're sitting in here. That's what I used to do. But for a while there, the streaming software, screen capture software I was using took too long to render. So I'd record it for 10 minutes, and then the rendering took 15. And you couldn't do any more recordings while that was happening. It's like, well, that's no good to me. I need it to be able to render in about a minute, 2 minutes. So the one I'm using now, Clipchamp, is pretty good. All right, so some simple geometry. So we've got an idea that we would have an x plus iy. That just gives us an x and a y coordinate. We can plot it anywhere on the 4 quadrants. Cool. Okay, some simple geometry. So we know about conjugates. If we have x plus iy, what is the conjugate of x plus iy?
X minus iy.
X minus iy. So we're just changing that. So if you think about that geometrically, if you've got x plus iy, you're in the first quadrant. If you then go x minus iy, where does it go?
Fourth.
So you think about it in terms of a transformation. What has it done? It's been reflected over the x-plane. Okay, so that's when you start to get a reflection over the real axis. So you look at some of the transformations you've done with polynomials and stuff like that. Now, don't forget, all of this is doable on Desmos and GeoGebra as well. They do have, you can do it on the real plane, you can do it on a Cartesian plane, but you do actually have access. They do complex number planes as well. So if you need to have a look at it and just double check things, it's on there. Cool. So the geometry of conjugates. So all it is, they are reflections of each other in the real axis. So it doesn't matter what quadrant it was in. You do the conjugate, it flips. Cool. All right. So now the opposite. So not the conjugate, the opposite. So z plus xiy, then the opposite is minus z, which is minus xiy, which is the minus of all of that. So what does it do?
It just
Wait.
There's 2 ways you can think about it.
it goes.
It flips along with the.
Tweaking. All right.
That
Yeah.
one.
It just goes like if you have the
It flips and then
X
flips, or you can say
equals
that it
Y line,
flips
it
along
flips
the.
along that line.
Yeah. So you've
Yeah.
got a couple of options. So you can say it reflects on the x equals y axis, so but depending on which axis it was in, it might go the other way. So it might go over the minus x equals y. Okay.
Wait, how is z equals x plus iy? Like, how is that opposites? Because you change all the signs. If you
Yes.
simplify it back, it'll be the same thing.
You got z
Surely it would just be
minus z
Yeah.
equals minus x plus iy.
Yeah.
Yeah.
So it's literally minus 1
Surely-
times it.
But like, if the
That's the
z is
same
also a
thing.
negative,
Mhm.
then would it not just be the exact?
Just to
same
simplify it, it'd be the same thing. Wouldn't it?
If I expanded that out, I get minus x minus iy.
Yeah.
thing? Yeah, but the
But you've got a
z is
negative
still
z.
negative.
Mm.
If you made the z positive, it's the exact same expression.
Yes.
So do you just
So-
not care about that?
So it's the same thing, isn't it? It's just a different.
Don't think of that as an operation. It's just showing if you have a complex number, the opposite of that complex number is just reverse the signs on both of them. So it's not doing the minus 1 times. It's just saying that's what the opposite is.
Oh, okay. Yeah,
Yeah.
sure. Yeah,
Oh.
that's fine.
So now what you've got is two different versions. You can either say it's flipped that way and then flipped that way. Okay, so you've got two transformations, both over the real and the imaginary axis, or you can say it's rotated around the origin, pi. Because twice around is 2 pi, because we talk radians. So it's rotated by pi around the origin. Okay, so that is the two of them. Now, I haven't written these down or highlighted them because you've got them in your books. At this point, this is where Michaela said, why is there 4 of them in a row? Yeah. So you can see these are just little bits of information. All right, sorry. Then the next one. All right. Imagine you had Z1 equals A plus IB. So you've just got one complex number equals that. Then Z and Z2 is I times that. So we're multiplying it by imaginary as well. Mm-hmm. That would be given by minus B plus IA.
Yep.
Yeah. So think about what has happened then.
The A is now imaginary, so the imaginaries become the real, and the reals become the imaginary.
Yes. So the imaginary become the reals become the imaginary. However, something else has happened with the real.
It's negative.
It's negative now. Okay. So what has that done geometrically? So we can see what it's done algebraically, but how do we think about this geometrically? This is what I love. I love the geometric side of things. So it is a right angle triangle. But how do we know that? How can we look at that, what they've done, and go, yeah, I can see why that is.
It's around the origin.
Right.
It shows the right angle.
You can see it on the board.
You can see it there. Is there any other way? It's a little bit abstract, but it's something I look at and go, hey, that's cool.
If you did, you could find out the side lengths.
Oh, yeah, you could.
Actually, no, I don't know if that.
Okay. What if I said, here is a gradient, here's a formula.
Yeah.
Would you agree that that is a gradient intercept?
Yes.
Okay. And from that is your gradient, correct?
Yes.
Okay. So if I had a line, and let's call it M, it's got a gradient of M1. Mm-hmm. Okay. And then if I times that, if I don't times it, what do I, if I said that equals 1 over minus, what am I trying to say? If I go M2 equals minus 1 over M1, the negative reciprocal.
Yes.
What is that?
It's perpendicular.
Yeah, that is, so M1 times M2 equals minus 1 is the definition of perpendicular gradients. Now, these aren't technically gradients, but if you have a look at that, can you see how you flipped them and one's now negative?
Yeah.
Okay, so if you switch them around, make one negative, one positive, they're going to be perpendicular to each other. Mm-hmm. Like it just feels as though they're going to be perpendicular. And that's the case. So what you've got, and this is, we have to put this caveat in, as long as neither A or B are 0. Okay, so if you've got 2 points where none of them, the gradients, and it does actually refer to the gradient of that one and the gradient of that one. Cool.
Yeah, sure.
So the gradient of them, and there it is.
Okay.
So because you're doing rise over run,
Yeah.
So you've flipped it and it's become that. So OZ2 is perpendicular to OZ1. And that gives you an anti-clockwise rotation. That's the other thing we think about it geometrically. So algebraically, we can see it's going to be perpendicular, but what has it actually done? It has rotated pi on 2 anti-clockwise. So 90 degrees, pi on 2. It doesn't matter whether it's real or imaginary as long as it's not zero.
Sure.
Next one, geometry of, so that's the multiplication by I. So, okay, let's do the worked example. I'll just hit hide on that so I can actually see it. Okay, let Z, so we're doing this one down here. Let Z equal x plus iy, determine iz, and hence give a geometric interpretation of the result. What I'm going to do is I'm going to pause for a sec so you guys can have a look at it. I just have to work out how to pause. Click. And, if I hit stop, is it going to stop? We'll see. If it stops, then I'll start it again. All right, so what I did was I paused it and now come back to it, and hopefully that means I'll be able to do longer ones. We'll see. All right. So what are we doing? Determine iz. So you're multiplying I times the conjugate of that. Now the not difficult, but the part that you need to get out of it is that last bit, determine it, and hence give a geometric interpretation of the result.
How?
Okay, so you did the conjugate, which means it's going to be a reflection.
Now, you guys don't have to listen to me. I'm sort of talking for Michaela here, talking for the ages. So when you're doing this sort of thing, when it wants you to do it geometrically, a geometric interpretation, a lot of times it is beneficial to draw yourself a little bit of a diagram so you know what's going on. So you have a look and you go, okay, we started off at Z. Okay, so we're trying to work out what has happened with Z. Hello? Yep. Yep. Yep, where are you? H8. All right, I'll send him there now.
So,
All right. So,
you're joking.
no, luckily, I'm recording this.
Oh, yeah. Thanks,
Wait, no, where are you going?
Caesar, I'm having fun one-on-one lesson. I don't know. I'm going to H8.
Yeah, H8 to see Mr. Brown.
Oh, he's going to make me do reader.
Almost
I'm going
inevitable.
to have to stay till 5 o'clock.
Oh, food tech, yeah.
Okay.
All right, mate.
Well,
good luck with it.
Yep. See you guys.
All
I
right.
know.
All right, now I'm talking to two people, but I'll post this up.
Yep.
Yeah. All right, so what we've got, like I was saying, it is sometimes easy to or helpful to give yourself a geometric interpretation. So you have a look and see what's done. Now you can see there, this is just Z with X and Y swapped. So we're starting with Z. Even though they've asked us to do I times Z conjugate, they've started with Z. So IY, we're in the positive. So all I'm going to do is put a dot there and go, okay, that's where we're starting. What have we done? You look at your result, and I've got Y plus X, IX. So all that's happened is my real and my real and my imaginary have changed. So I'm actually going to put it down there so I can sort of see that where the real and the imaginary are. So my real is there, my imaginary is over there. So what has actually happened? It's gone over here. Okay, and so you think, oh, how has it flipped? Right. Was it there? Hang on. No, it's not. No, it's not. No, it's not. It's there. Stop that. It's just up there because it's still both positives. So I'm still in that first quadrant, which means it has flipped on that line. It's just gone straight over that. That makes sense? So sometimes when it's asking for a geometric interpretation, it's really handy to have geometry there to help you.
So, where is the first point, the Z equals X plus IY point?
There.
There?
Yeah.
So is it at,
I'll zoom in.
like X is 1?
Yeah, what I've done, because we didn't get given anything, so what I've done is I've gone, okay, let's make X2 and then Y1. Right. I've just done it that so that because if I did it on the 45 degree, it wouldn't have moved.
Yeah.
Because the X and the Y would have been the same, so you wouldn't have seen the swap.
That's why I was.
Yeah.
I had mine just right in the middle.
Yeah, I know. And that is one of the problems. When you're doing these, sometimes it's easy. So it's habit to put it pretty centered. So I deliberately had to make myself put it so that the X and the Y had distinct values so that you could see it a bit more clearly. Cool bananas?
Yeah.
All right. Curves in the Argand diagram. So at the moment, we've been doing just individual points. We haven't worried about curves. But often an equation in Z will correspond to a well-known line or curve in the Argand diagram. All right. So here is a couple of well-known curves and that. Real Z. 2.
Yeah.
Okay. That is literally just the real is 2, therefore you go across to the real and you draw on a vertical line. Okay. Imaginary is -1, exactly the same, but you go to imaginary, go down to -1. So these are the equivalent of vertical and horizontal lines, obviously, on the normal Cartesian plane where x equals 2 or y equals -1. Cool. Pretty straightforward. If you want to then find where they intersect, same as any other one, you find the point, where do they intersect? They intersect at 2 minus I. Okay, z equals 2 minus I. So you could pull the coordinate and go, well, they're meeting at 2 minus 1. Oh, I don't know why I drew it up there. They're meeting at 2 minus 1. That's the point that they're meeting at. But then when you put it back into this form, you get that. Cool. All right. So that's vertical and horizontal lines. All right, there we go. Let the point P in the complex plane represent the number Z equals IY. They say that a lot. It's common for them to say that because they're setting it up. So there's a point P. Given that Z times the conjugate of Z equals 9, find the curve that P is on and sketch it.
Okay.
What I want you to do is, you know what Z is. You know what conjugate of Z would be. Multiply them together, see what happens.
Oh.
Okay?
Yeah.
Michaela and Noah are now sitting there listening to absolute dead silence. Can they? Is it paused? Has it crashed? No, maybe it has. Who knows?
Maybe.
They'll never know.
Surely that's just the equation for a circle.
Oh, well done. So you got x squared plus y squared equals 9?
Yeah.
And equation for a circle is x squared plus y squared equals r squared. So draw me the locus of those points. Circle centered on the origin, radius 3.
Yeah.
So that's literally what you had to do. You had to find that and sketch it. I'm assuming you sketched it. All right. So in some examples, it is best to manipulate the given equation in Z first and then substitute x plus iy. Yes, that is very handy sometimes. It's also important to note any restrictions on Z before starting. Both of these points feature in the following example. So that one just expanded out. Like, it was great. But let's see what happens in these next ones. All right. Find and describe the curve specified by that.
Okay.
So when we look at that, we go, okay, let's think about some of the limitations that we're going to have.
Z can't be 0.
Z cannot be 0.
Conjugate of Z can't be 0 either.
Cool. And now, well, the conjugate of Z won't be 0 if Z's not 0.
Yeah.
So what do we do? Remember that it said sometimes it's easier to manipulate it in Z before you do anything else.
Is Z just X plus IY?
That is, but it might be easier to work with just Z for a while.
Just oh yeah. Okay.
Why?
Because you can get it all in the fraction.
Yeah, I don't like fractions so much.
No,
I don't have common denominator.
Yeah, you can get a common
So let's get it so that we don't have fractions anymore. Because you're going to have to do that anyway. But once you've got X plus IY, you're starting to do it with multiple terms, and then you've got the complexity of that. So what do we do?
Yeah, you multiply 1 on Z by the conjugate of Z. Right. Then...
So basically, you're going to multiply by the common denominator, which in this case is Z and the conjugate of Z. Yep. And that means you'll end up with Z, the conjugate of Z plus Z equals the multiplication of. Okay, it's standard fractions. And it's weird because you think, why would I be doing standard fractions? This is complex numbers. So I don't care. The good thing, the wonderful thing about a lot of this stuff, even though it's much more complicated maths in a way, is it's still using adding, subtracting, multiplying, dividing. It's using the processes that you've learned since year 7.
Mm-hmm.
Okay, so you cool with that bit?
Yeah.
Then you sub it in.
Okay. Right.
Okay. So they have skipped, and this is where I was talking about sometimes this will skip.
I won't skip.
So you're basically doing X plus IY.
Yeah.
X minus IY plus X plus IY, which obviously cancels out the IYs, which leaves you with 2X.
Mm-hmm.
And then we've already done that sum of 2 squares from the previous question.
Yeah. Yeah. Equals 0. What did it do there? It has... Oh, I see. Oh, has it completed the square?
Yep.
Right. Yeah. Okay. This one's square root. And we've just got a circle again.
But
it's not. Huh?
It's not centered.
Yeah.
So you got the X minus 1, which means it's shifted one positive.
Shifted 1, and radius is 1.
Yeah. Spot on.
Yeah.
Awesome. Well, that's going to do it. So we can say goodbye to Michaela and Noah.
Yes. Bye,
I'm recording for them. I've just got to remember how to get back. There it is. All right.